So in this lesson, we're going to introduce what is really just a trick for evaluating limits. It is called Lhopital's rule, not to be confused with the hospital rule. And we're going to build towards this idea so you kind of understand where it comes from. To start, we're going to sort of remind ourselves of some of our old strategies for evaluating limits and investigate why we couldn't solve this limit right here in part B. So first we're asked to evaluate f of 3 and g of 3, and you can check on your calculator, but we get 0 for both of these. So f of 3 is 0 and g of 3. And the reason we cannot evaluate this limit by direct substitution is this would be equal to the limit as x approaches 3 of f over g, which would give me 0 over 0. So direct substitution, of course, means to plug in a value, right? So this is the reason why. And the vocabulary term for this is that we get an indeterminate form. And indeterminate form is just fancy word for, in this case, we get 0 over 0, which is kind of meaningless. We know dividing by 0 doesn't mean anything in mathematics. And then we're asked to use the factoring method, which is something that we covered last year in pre-calc, which means we rewrite the limit as the limit of the factored form. So I'm going to factor the top. The bottom is obviously already done. And then I notice that something can cancel, and I'm left with x plus 5, and then I can evaluate by substitution. That's just equal to 8. So there is my solution, and that is an old method that we've used for limits. However, now that we know how to take a derivative, we can take the derivative of the top and bottom. We're going to notice an interesting pattern here. So we're asked to evaluate the limit of f prime over g prime, and f prime would be 2x plus 2, and on the bottom, the derivative of g prime is just 1. And notice we're not taking quotient rule, right? We're not asked to take the derivative of the whole function top and bottom together. We're asked to take the derivative of the top separately from the bottom. And notice this one I can now evaluate by direct substitution, right? 2 times 3 plus 2, well, is 6 plus 2 is also equal to 8. So that's a really interesting result here. So the result was that when we take the derivative of both the numerator and the denominator and then try to take the limit, we get the same thing as with our old method. Now, this is a rule. And often when we have rules in mathematics, we just kind of learn the rule and we learn, oh, this is a nice trick, but we don't really learn how it works. But I want to think about this just a little bit more deeply, right? Just to consider why this rule might work the way it does. Now, this is not going to be a formal proof of the rule or anything, but it will help you build some intuition for it. So the question is, how do values of f of x and g of x at x equals 3 compare? So we saw that they're the same, right? But then when we consider which function is changing at a faster rate at x equals 3, well, we got the f prime of 3 was 8, but g prime of 3, well, g prime of anything, is 1. So why does this matter, right? Well, if f has a bigger growth rate, it will also have a bigger effect on the limit of the two functions. So another way to interpret our limit, right, is how is the ratio of the two functions changing at that value? And the answer to that question can help us take the limit when we get a result like 0 over 0. Now, this rule is for all limits with indeterminate forms. There are two indeterminate forms. 0 over 0 is one, and another indeterminate form, infinity over infinity. So it makes sense that we call it an indeterminate form because both of these ratios don't really mean anything, right? So it's like infinity over infinity if it were a number, it would be 1, but it's not. It's like infinity is not a number, it's a concept, right? So we have these two situations in which this rule is useful to us. And then the rule is take the derivative from the top and bottom and then try to plug in your value again. So here, first I would say e to the 0 minus 1 over sine of 0, well, is 1 minus 1 over 0 is 0 over 0. So then I have an indeterminate form, and then I can't factor and cancel here, right? Because these functions are not algebraic. But I can take the derivative of the top and bottom. So I'd say is equal to the limit as x approaches 0. And here's where you see if you really did remember all those rules. Well, on the top, I get just e to the x, because that's the derivative of e to the x, and the derivative of negative 1 is 0. On the bottom, I get cosine of x. Now, here, I can plug in my 0. So I get e to the 0 over cosine of 0. And I get 1, anything to the 0 is 1, and then cosine of 0 is also 1. So I get 1 here would be my final answer. So that is a scary looking limit that we actually just made really easy with our knowledge of our derivatives rules. Now, this also works when you're given functions in more interesting ways. So here we have this crazy looking function where we have an algebraic function on top, and then we just have a function f of x on the bottom, and there's some stuff happening to it, and f of x is the graph. The first thing I would note would be like f of 0 is 0, right, from the graph. So if I plugged in 0 to this whole thing, I would get 0 over 0 would be my limit, right? You can check 3 times 0 minus 5 times 0 is 0, and then 3 times 0 minus 3 times 0 is still 0, right? So my limit would be equal to the limit as x approaches 0 of 6x minus 5, and then 3 times f prime of x minus 6x. Right, so I just took the derivative of the top and bottom, and now I definitely don't get 0 on top anymore. And then for the bottom, well, my slope here looks to be negative 3 over 1, right? So that would be f prime of x. So my limit is equal to 6 times 0 minus 5 over 3 times negative 3 minus 0. And here I get negative 5 over negative 9, or 5/9. Okay, so it's a really versatile rule because it allows us to tackle both non-algebraic functions like this and more complicated limits involving graphs like this.